Absolute value inequalities. An absolute value inequality is an inequality that contains an absolute value expression. We're going to show a few examples, including graphs of their solutions. So in example A, we have that the absolute value of x is less than or equal to 2. This absolute value inequality is equivalent to negative 2, which is less than or equal to x, which is less than or equal to 2. You could also state this compound inequality as x is greater than or equal to negative 2 and x is less than or equal to positive 2. You could also write it as an interval. So x is contained in the set of numbers between negative 2 and positive 2, including both endpoints. And the solution is the set of all x values between negative 2 and positive 2 inclusive, meaning it includes both endpoints. Here's another example. This time we have the absolute value of x is greater than 3. So this absolute value inequality is equivalent to x is less than negative 3 or x is greater than 3. And again, that's as a compound inequality. It could also be written in interval notation as x is contained in the set of numbers from negative infinity to negative 3 in union with positive 3 to positive infinity. And the solution set is the set of all x values that are more than 3 units away from the origin. The absolute value inequality of the form, the absolute value of the quantity x minus c is less than or equal to d, where d is a positive number, meaning greater than 0. That's equivalent to x minus c being greater than or equal to negative d, and x minus c has to be less than or equal to positive d. In other words, if your absolute value inequality has a less than or equal to sign, it will produce an and compound inequality. Notice less than ends with an an and begins with an. So that's a way to make a connection between what type of inequality it produces. And then when a c is added to each side of the inequality, you'll end up getting c minus d is less than or equal to x, which is then less than or equal to c plus d. You could also write it as x is contained in the set of numbers between c minus d and c plus d. Notice we have closed circles because this one had an equal to in it, and we shaded in between, including our center. And the solution set is the numbers x that are between c minus d and c plus d, including both endpoints because we have the equal to. The absolute value inequality of the form, absolute value of the quantity x minus c, is greater than or equal to d, where again d is a positive number, meaning greater than 0. It's equivalent to writing the compound inequality x is less than or equal to c minus d, or x is greater than or equal to c plus d. And the connection between this is we have our inequality when it's greater than. It ends in an ER, which sounds a lot like or. Sometimes we can also write it as great and then OR in caps, signifying that the arrows, when drawn on the number line, are going to go in opposite directions. When writing it in interval notation, it will be that x is contained in the set of numbers between negative infinity to c minus d. Because we have the equal to, we have a closed bracket in union with another closed bracket from c plus d to infinity. So the value of the absolute value of the quantity x minus c represents the distance a number x is from a fixed center point or number c on the number line. Also, the inequality, the absolute value of the quantity x minus c, being greater than or equal to d, means the distance a number x is from the center point C on the number line must be greater than or equal to the number D. So it's got to be at D and beyond. Here are two examples where we are solving absolute value inequalities and graphing the solution set on a number line. The first one that we have is the absolute value of the quantity x minus 2 is less than or equal to 4. If you'll recall, absolute value inequalities that contain a less than sign or a less than or equal to sign produce an and statement. So you could write either one long compound inequality, such as -4 is less than or equal to x minus 2, which is less than or equal to 4, or you could write it out as two separate inequalities with the word and in between them. So you could have that x minus 2 is less than or equal to 4 and x minus 2 is greater than or equal to -4. Notice that this compound inequality that we have over here to the left means the same thing as the two sets of inequalities that we have here to the right. So let's begin solving. To do this, we would add 2 to all sections of the inequality. So there's a side over here, there's a section in the middle, and there's a side over here. So we would have -2 is less than or equal to x, which is less than or equal to 6. And if we solve both of these here to the right, we would get the same answer. We would add 2 to both sides here, and we would get that x is less than or equal to 6, this right half of the compound inequality. And if we add 2 to both sides here, -4 plus 2 gives us -2. So x has to be greater than or equal to -2. And that's this section. So again, you can solve it either as one compound inequality, or you could solve it as two separate inequalities with an and in between. So now let's graph the solution on the number line. So we have -2, -1, 0, 1, 2, 3, 4, 5, 6. And then we have greater than or equal to -2. So it's going to go in this direction, and it's less than or equal to +6. So we have 2 filled in circles, and we're shading in between these two x values of -2 and +6. Now let's look at example D. So example D, we have the absolute value of the quantity 5 minus x is less than 3. And since we know that one of the properties of absolute value is that you can switch around the order in subtraction and still get the same absolute value, let's actually do that to make the inequality solving a little bit easier. So we now have the absolute value of the quantity x minus 5 is less than 3. Again, since we have a less than symbol, less than produces an and statement. So you can write it as -3 is less than x minus 5, which is then less than 3. Or you could write it as a compound inequality with the word and in between. So you could have that x minus 5 is less than 3 and x minus 5 is greater than -3. And now we can go forward or move forward and solve each of these inequalities. If we do it with the 3 sides of the inequalities, we would add 5 to all sections. And when doing so, we will end up having 2 is less than x, which is less than 8. If we solve them individually, we would again add 5 to both sides, and we would get that x is less than 8. So that gives us this right section of our compound inequality. And if we add 5 to both sides of this inequality, we would end up getting that x is greater than +2. That gives us this side of our compound inequality. So now let's graph this on a number line. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And now our two endpoints are 2, and it's an open circle because there is not an equal to sign. And 8 is our other side. And because it's an and statement, we're less than 8, so that's to the left of 8, and we're greater than 2, so that's to the right of 2. So we just fill in the section in between them. Now, since we've also been talking about interval notation, you can also rewrite both of these solutions as an interval. So for example C, our interval would be that x is contained in, these are closed brackets from -2 to 6. And for our second example that we did, or example D, we could write that x is contained in, this time with open parentheses, the set from 2 to 8. And here are the solutions to the two examples that we just worked out, and the solutions found are exactly the same as what we found when we worked through the problems together. It's also important to note that within the absolute value inequality, you can also mark the center point, which is 2 for the first one, and then you can go 4 above and 4 below graphically. And that's another way to think of the solution set from -2 to +6, including both endpoints. And similarly, because we switched around the x and the 5 in the subtraction, because absolute value allows us to do that, again, it only works in absolute value, we have now that our center point is 5, and the distance from our center point to each endpoint is 3 units. And we shaded in between because it was a less than sign. So we have our solution, x is contained in the open interval from 2 to 8 for this problem solution. Now let's go over 2 more examples. In these, we are provided a graph of the solutions of an absolute value inequality. So this time we have an and statement, and down here we have an or statement. We have to determine what absolute value inequality will model each of our graphs that are provided. And there are a couple of different ways that this can be approached. If you look at it visually or graphically, we can clearly see in example E that our center point is -1.5 or -1.5. And if you remember, in an absolute value inequality, we take our x value and subtract that center point from it. And because it's an and statement, we need to have a less than sign. And now we have the distance is what appears on the other side of the inequality. So we have to go a half, 1, 2, 3, 4. So we have to go 4.5 units to get from our center to each edge, a half, and then 1, 2, 3, 4. And then if we simplify this and get rid of the double negative, we would have that the absolute value of x plus 1.5 is less than 4.5. That's the approach graphically. Now let's look at it algebraically. We can see from the original graph that our x value has to lie between -6 and +3. From here, we can still see in our graph that our center point is -1.5. So if we subtract -1.5 or add 1.5 to all 3 sections of our compound inequality, we will end up getting that x is between, x plus 1.5 is between 4.5 and -4.5. So because the both of these endpoints are identical, we can then write it as an absolute value. So it's the absolute value of x plus 1.5 is less than 4.5. Now let's look at the next problem. If we first approach it visually or just by observing the graph, we can see that this is an OR, which means that the absolute value must be greater than, and now these are open circles, so there is no equal to, and we have an x minus, what's our center point? Our center point is right here at negative 4.5. And then it's greater than, what's our distance from our center to each endpoint? Well, we have to go a half and then 1, 2, 3. A half and then 1, 2, 3. So it's greater than 3.5. And then if we simplify by changing the subtraction of a negative to a plus sign, we get that x plus 4.5 inside the absolute value must be greater than 3.5. So this is the final answer. If you like to approach this algebraically, instead of just observing the graph and directly putting it in absolute value terms, we can do that. So we know that x has to be less than negative 8 or x has to be greater than negative 1. If we subtract our center point from all sides of these two inequalities, and our center point is negative 4.5, so we're subtracting negative 4.5. Wait, that means adding. So we're adding 4.5. We're doing that to all sides of our inequalities. We will end up getting that x plus 4.5 is less than negative 3.5, or x plus 4.5 is greater than positive 3.5. Notice we have the opposites here and the same exact expression on the left side. So that is why we can write it as the absolute value of the quantity x plus 4.5 is greater than 3.5. And here are the solutions to each of these absolute value inequality graphs. It does model that the absolute value of the quantity x plus 1.5 is less than 4.5. And this one right here in example F models the absolute value of the quantity x plus 4.5 is greater than 3.5. We have recently gone over how absolute value inequalities are related to compound inequalities. You can also do this in a two-dimensional graph or using the two-graph method. So to solve the inequality f of x is less than g of x means to find all of the x values where the graph of f of x is positioned below the graph of g of x. So in this graph right here, the absolute value of x minus 2 is less than 4 from negative 2 to positive 6. We're finding what is less than 4, so below our horizontal line, and where f falls within this interval. So that happens from negative 2 all the way up to positive 4, and we're not including both endpoints because there's no equal to in our original inequality. So that's how we get the solution that x is contained in the open interval set from negative 2 to positive 6. We're using the x-coordinates of our points of intersection. If we were solving an inequality where f of x is greater than g of x, then what we would be doing is we would be finding all points where f of x lies above this line. So in this problem, it would be from negative infinity to -2 in union with 6 to infinity. And it means finding all of the x values where the graph of f is positioned above the graph of g. Now let's discuss modeling with absolute value inequalities. Modern hot water heaters are designed with a thermostat to heat water to safe levels. The standard thermostat maintains the water temperature within 3 degrees of 118 degrees Fahrenheit. We need to sketch a graph and write an absolute value inequality that gives the range of water temperatures, capital T, that is consistent with the standard hot water heater thermostat. Well, within 3 degrees of 118 degrees will give us the compound inequality that x is between, or I'm sorry, capital T instead of x, is in between 3 degrees of 118. So if we add 3 degrees to 118, we get 121 degrees. And if we subtract 3 degrees from 118 degrees, we end up getting 115 degrees. This temperature model compound inequality is shown in this graph. Now, how do we write this as an absolute value inequality? Well, we can also tell that from 115 to 121 degrees, our middle point is 118. Oh, hey, that gives us the starting value that we had from this word problem. That's our center point. So that means we have that capital T minus 118. Because this is an AND statement, it's less than, and then the circles on both ends are filled in, which means equal to. And now the question is, what number goes over here? Well, it's within 3 degrees. That tells us the constraint, or what number the absolute value inequality is related to, or the number that goes on the outside of the absolute value inequality. Another way to think about this is if we start with our original compound inequality that we had here, we could subtract 118 from all of these. And when we do that, we would have -3 is less than or equal to T minus 118, which is less than or equal to 3. Notice that -3 and +3 both have an absolute value of 3. And our T minus 118 degrees is between -3 and +3, which means the absolute value of it will be less than or equal to 3. So that's how we get this absolute value inequality, both graphically through graph analysis and algebraically. And here we see the solution to the graph and compound inequality, and then the final absolute value inequality to model this example. And the solutions found do match the solutions that we found when we worked it out. Let's try another example where we are modeling with absolute value inequalities. Every year, the state fair holds a competition to grow the largest pumpkin. In recent years, the champion pumpkins have weighed within 340 pounds of 1,180 pounds. Sketch a graph and write an absolute value inequality that gives the range of the champion pumpkin weights, capital W. All right, so instead of just having a random variable x, we're going to have a capital letter W. So the champion pumpkins have weighed within, so that's the amount that we are going to add and subtract from or to 1,180 pounds. So if we add 340 to 1,180, we would end up getting 1,520 pounds. And if we subtract 340 from 1,180 pounds, we would end up getting 840 pounds. So therefore, the acceptable weights, or the weight range of champion pumpkins, have been between 840 pounds and 1,520 pounds. So a graph of this would look something like this. We have 840 and 1,520. We have both endpoints included, and we are shading in between because our weights could be equal to each endpoint or lie in between. Now, how do we come up with the absolute value inequality? Well, it can be done by finding our center point or by also looking back in the problem. Well, we added and subtracted 340 pounds to 1,180 pounds. So that's our midpoint, or our center point. It's 1,180. So that means in our absolute value inequality, we will have capital W minus 1,180. And because it's in between, the absolute value is less than or equal to, and then the pounds that we added and subtracted, that's our constraint that tells us what that highest value or lowest value can be. So it's going to have to be less than or equal to 340. And if you actually rewrite this out as two inequalities and solve for W, you will end up getting this exact compound inequality. And here's the solution. And the number line that we drew does match the number line that we had. And we always had 1,180, and we subtracted 340 from it, and we added 340 to it. And then if we were to actually take 1,180 and subtract it from all 3 points, we would get W minus 1,180 is less than or equal to 340 and greater than or equal to negative 340, which then allows us to write it as this absolute value inequality, which is the absolute value of the quantity W minus 1,180 is less than or equal to 340.